Hello. Consider the function g defined as follows: g of x is 3x cubed plus 9x squared plus 2x plus 6 over negative x minus 3 for x less than negative 3, and g of x is 2bx squared plus cx plus 5 for negative 3 less or equal to x and x less than negative 2. Moreover, g of x is x squared plus bx plus c for x greater or equal to negative 2. We will try to find the values b and c that make g continuous everywhere. The function g is obviously a piecewise rational function. This means that each piece of this function is continuous on its interval of definition. It remains for us to check the continuity of this function at the end points of these intervals. So we will study the continuity of g at the points -3 and -2. The function g of x is continuous at x equals -3 if and only if the limit of g of x as x approaches -3 is equal to g of -3. Likewise, the function is continuous x equals -2 if and only if the limit of g of x as x approaches -2 is equal to g of -2. Remark that the limit of the function exists if and only if the left-hand limit and the right-hand limit exist and are equal. Therefore, we should start by evaluating the one-sided limits of the function as x approaches -3, and x approaches -2. We will first compute the limit of the function as x approaches -3 from the left. Given that when x is less than -3, the function g of x is equal to the fraction 3x cubed plus 9x squared plus 2x plus 6 over -x minus 3. Therefore, the left-hand limit of the function as x approaches -3 is the limit as x approaches -3 of the fraction 3x cubed plus 9x squared plus 2x plus 6 over -x minus 3. Let us compute the limit as x goes to -3 of the fraction 3x cubed plus 9x squared plus 2x plus 6 over the polynomial -x minus 3. It is better to start by finding the value of the fraction at the point x equals -3. After evaluating the fraction at the point -3, we have -81, plus 81 minus 6, plus 6, over 3 minus 3, which equals 0 over 0. We obtain an indeterminate form of the type 0 over 0. This means that, we have to factorize the whole fraction in order to simplify the common factor. This occasionally happens when the quantity x plus 3 is a common factor of both the numerator and the denominator. The polynomial 3x cubed plus 9x squared plus 2x plus 6 is divisible by x plus 3, since they have a common root, -3. When we divide 3x cubed plus 9x squared plus 2x plus 6 by x plus 3, we get 3x squared plus 2. Therefore, 3x cubed plus 9x squared plus 2x plus 6 can be written as the product of x plus 3 and 3x squared plus 2. We notice that the numerator can be factorized as the polynomial x plus 3 times the polynomial 3x squared plus 2. And the denominator can be factorized as the polynomial x plus 3 times the polynomial -1. The common factor in both expressions that should be simplified is x plus 3. By replacing -3 in this new function, we find that the limit is -29. The limit of the function g of x when x goes to -3 is -29. Now, let us evaluate the limit as x approaches -3 from the right. We know from the definition of the function g that when x is greater than negative 3g of x is 2bx squared, plus cx plus 5. Therefore, the right-hand limit of the function as x approaches negative 3 is the limit as x approaches negative 3 of 2bx squared, plus cx plus 5. Which is equal to 18b minus 3c plus 5. For the function to be continuous at x equals negative 3, we should have, minus 29 equals 18b minus 3c plus 5. We will now determine if the function g of x is continuous at x equals minus 2. We will therefore analyze the left-hand and right-hand limits at this point. Next, we will compute the left-hand limit of the function as x approaches negative 2. Given that when x is less than or equal to negative 2, the function g of x is equal to 2bx squared, plus cx plus 5. Therefore, the left-hand limit of the function as x approaches negative 2 is the limit as x approaches negative 2 of 2bx squared, plus cx plus 5. This limit equals the value of the function 2bx squared, plus cx plus 5 at the point negative 2. This equals 8b minus 2c plus 5. Now, we will compute the right-hand limit of the function as x approaches negative 2. It is clear that when x is greater than negative 2, the function g of x is equal to x squared, plus bx plus c. Consequently, the right-hand limit of the function as x approaches negative 2 is the limit as x approaches negative 2 of x squared, plus bx plus c. This limit equals the value of the function x squared, plus bx plus c at the point x equals negative 2. This equals minus 2b plus c plus 4. For the function to be continuous at x equals negative 2, we should have 8b minus 2c plus 5 equals, minus 2b plus c plus 4. We have the following system of equations. Minus 29 is equal to 18b minus 3c plus 5. 8b minus 2c plus 5 equals, minus 2b plus c plus 4. We will now solve this system of equations to find the values of b and c that make the function g continuous everywhere. We simplify these equations and obtain 18b minus 3c plus 34 is equal to 0, and 10b minus 3c plus 1 is equal to 0. In sum, for the function g to be continuous everywhere we need to find the values of b and c that satisfy the following system of equations. 18b minus 3c plus 34 is equal to 0. 10b minus 3c plus 1 is equal to 0. We will now solve this system of equations to find the values of b and c that make the function g continuous everywhere. We solve the first equation for c. This allows you to express c in terms of b, and replace this new expression of c in the second equation. The value of c is 34 over 3 plus 6b. We substitute this value of c in the second equation and obtain, minus 8b minus 33 is equal to 0. We solve the second equation for b, and find that b equals minus 33 over 8. Finally, we substitute the value of b in the expression of c to find the real value of c. This gives us c equals minus 161 over 12. Therefore, the values of b and c that make the function g continuous everywhere are b equals minus 33 over 8, and c equals minus 161 over 12.